So today I will talk about reinforcement learning, and I will discuss some of the theoretical challenges we have when moving from reinforcement learning with single agent to many agents. And we'll also discuss how we address some of these challenges there. Okay. And if you have any questions throughout the talk, feel free to interrupt me, given that we're a small group. Yeah, don't hesitate to just unmute yourself and interrupt me, okay? So I hope you all agree with me that reinforcement learning is really one of the main driving force behind many of the AI breakthroughs recently, particularly those make artificial intelligence more powerful in decision-making, not just in pattern recognitions. And one of the earliest breakthrough in reinforcement learning actually dates back to the 1990s for the game called backgammon. And back then, an IBM researcher, Gary, developed a computer program based on some reinforcement learning algorithm that is able to achieve a play only slightly below the best human player at the time. And what's already interesting back then is that the computer program is able to explore strategies that humans has never explored. And of course, now that 30 years later, we have witnessed a boom of all kinds of successes of reinforcement learning in playing all sorts of video games, board games, and for achieving superhuman intelligence. And recently, the success has further expanded to more scientific domains, such as, the design of novel matrix multiplication algorithms by alpha tensor, or, the nuclear plasma control, right, for nuclear fusion. And also, not to mention that recently that there is also fresh breakthroughs that reinforcement learning-based agents managed to achieve gold medal standard for solving IML problems. In a nutshell, I would say that reinforcement learning is all about making good decisions by learning from experiences in an uncertain environment. As a refresher to many of you, right, in the canonical settings, oftentimes we assume that the agent observes some state information from the environment, and the agent could choose certain action from some given action set, upon which the environment...
Niao, sorry that I interrupt you, but I'm not sure if it's only me that sees only part of your slides. So it's not really centered. Maybe...
Let me just reshare. That's okay. Can you check if it's better?
It's still, maybe if you can move it a bit to the left. I don't know, do you see it also like that, or...
It's okay from my end.
Okay.
Is it full screen or is not?
Okay, so yeah, I could actually move it myself. Okay, sorry.
Okay, that's great.
Yeah, sorry to interrupt.
No worries.
Problem at all, yeah? All right. So as we know that in the canonical settings, usually an agent can choose an action given some actions set, and then the environment will then, based on the action that the agent takes, will return some changed state information, and also will return to the agent some reward signals or reward feedback. And in general, for the state action and also reward composition could vary significantly across different applications, right? In some applications like games, oftentimes the state and action space can be discrete and huge. And oftentimes we can observe very frequent rewards from the environment. In other applications like self-driving cars, the state and action spaces could be continuous and reward could be more sparse. So at the mathematical level, oftentimes we denote the agents or the decision maker's behavior as a policy pi, right? This is a mapping from the state space to the action space, or the probability space, or the probability over the action space. And the environment is oftentimes captured by some model or Markov model oftentimes, and this captures basically the state transition dynamics P and also some reward function R. And in reinforcement learning, oftentimes the model is unknown, which makes it very different from like traditional optimal control problems. So at every time interval, at every round, An agent will observe some state ST from the environment, and then it will decide to take some action AT following this policy pi it has in mind. And based on which the environment will then return to a new state, ST plus 1, following some state dynamics P, and it will also return to the agent some reward RT. Okay, so in general, for a given policy pi and some initial state S, we can denote or we can define this cumulative reward over time as the so-called value function, which we denote as V pi here. Okay, and these three components, the policy, the value, the model, basically consist of the three most basic components of reinforcement learning. And the goal of reinforcement learning is oftentimes to find out what is optimal policy that maximizes long-term cumulative reward, right? And this naturally reduces to some optimization problem where we try to maximize this value function V pi over some admissible policies. Of course, this is a very challenging optimization problem because it can be both high dimensional and also at the same time heavily non-convex. So what is the current kind of nuts and bolts of modern reinforcement learning solutions? How do they cope with these challenging optimization problems? Of course, the kind of the common practice and black magic of all time combine the classical reinforcement learning algorithms or dynamic programming algorithms with deep learning techniques. Here we use deep neural networks to represent the policies or values or models in order to handle extremely large scale systems. The combination of these two, reinforcement learning and deep learning, is of course so-called deep reinforcement learning. And this is nothing new, right? This is already something that has been explored over 30 years ago for the game like backgammon. So what has changed since then? Of course, one difference clearly is that now we're able to, deploy much more sophisticated neural structures or foundation models. We're able to accelerate the training using GPUs. But another key difference, I would say, is that the introduction of various algorithmic techniques or engineering tricks that makes the training of deep reinforcement learning more stable, more robust in practice. As we all know that neural networks can be very brittle. And there are many techniques like experience replay, entropy regularization, double learning, so on and so forth. An interesting phenomenon in practice that oftentimes the more ingredients you mix into the plate, the better performance you get, right? In practice, people simply use deeper neural networks using, adding more and more tricks and burn more GPUs to train large models. And oftentimes they get better performance. In a way that the field, and just to give you an example, for example, for the rainbow agent that was developed by DeepMind several years ago, that if we simply just top up all the tricks that was used for different variations of DeepQ networks algorithm, then we can achieve already a significant boost among all these other algorithms, as you can see. And this is not a single observation, right? This has been observed in many applications as well. So in a way that the field has become overly reliant on empirical exploration and brute force computing powers. And what's clearly missing in the plate is, of course, the science and also the fundamental principles behind it. And I think we currently lack a very solid understanding of when and why and to what extent what these algorithms work and when it doesn't work. So that what I mean by that's what I would say is one of the grand challenges with deep reinforcement learning nowadays. The second grand challenge, I'd say, is the need for scalability. And we're not speaking only about reinforcement learning systems that has a significant number of agents, but we're also talking about systems that oftentimes involve a large number of agents, or systems where we want to train agents to solve many, many different tasks. And as the size of the states and agents and tasks grow, then the amount of compute we need and models we need grows also significantly. If you ask ChatGPT, say, how much does it cost to train AlphaGo 0? Of course, they will tell you that there is no specific public figure yet, but it will give you some rough estimate. And particularly, it will tell you that, to train this AlphaGo Zero, it would roughly cost $35 million and would consume 28,000 kilowatt hours. And if you're not sure what this means, this is roughly how much 32 households would consume in 1 month, and that's a lot. And if you only have one NVIDIA, like A100 GPU, like many standard labs have, then you probably will have to train this for over 10 years. Of course, we should always take a grain of salt with whatever ChatGPT tells you, but you kind of get the point here. So in this talk, I'm going to try to bring in some new perspectives on the principles and scalability, particularly for many agent reinforcement learning. And as I mentioned earlier, with the expanding reach of reinforcement learning towards more and more real-world applications, oftentimes we have to deal with systems that involve many agents. And these agents could be cooperative or competitive, right? In the cooperative settings, agents can communicate and coordinate with each other to achieve some shared common goal. And this is largely related to, say, distributed optimization, and you can find some recent advances that's summarized in the following survey here. In the competitive setting, the situation is different, right? In the competitive setting, oftentimes agents learn some policies that are self-interest in order to maximize individual rewards. And the goal there is then to seek to compute some kind of equilibrium. And that is what I'm going to focus more on this talk for today. So there has been actually significant progress in the theoretical side for these competitive games in more structured settings. For example, the zero-sum Markov games and also the Markov potential games. And in this talk, I'm going to focus more on the many agent setting without imposing any structure like zero-sum structure or potential structure. We're going to just consider reinforcement learning systems where there are many agents involved. Of course, applications involving many interacting decision makers are everywhere and span a wide range of application domains. For example, to model, say, social networks, online bidding, or smart grid, or all the way to, say, the modeling of brain activities or animal herding effects, right? In many of these systems, you can imagine that the number of agents or decision makers involved can be huge. So despite these many applications, solving these many agent reinforcement learning problems is notoriously hard. And this hardness comes from several curses, right? The first curse is due to the curse of multi-agency. As we know that the size of state action space will scale exponentially with the number of agents. So the more agents we have, then the larger the policy space we need to deal with. The second curse comes from the curse of tractability, or more on the computational side. And as we know that even without state dynamics, right, just computing, say, for example, Nash equilibrium alone for general sum games is known to be a PPAD complete problem. And if you're not familiar with this PPAD completeness, this basically, it is conjectured to have no polynomial time algorithms there. Lastly, as I said, we're interested in this competitive setting, then oftentimes agents are not allowed to really communicate or coordinate with each other. And recently it has been shown that if we let agents to play independently with some no-regret learning algorithms, and this no-regret learning algorithm is perhaps the most kind of rational assumption for the most natural assumption for rational behaviors in the online learning setting. And if we just let agents to play independently while no-regret learning, it has been shown that it is computationally and statistically intractable for agents to learn the corresponding Nash equilibrium, or even weaker notion of Nash equilibrium, such as coarsely correlated equilibrium. And this holds true already in 3-player Markov games, not even to mention when the number of players is large. So at this point, of course, the problem sounds quite scary and hopeless to solve. And as a theoretician, we know that if a problem is too hard to solve, what should we do, right? We should either, change the assumption, or we could just change the solution concept here, right? And this is what we're going to go after for this talk. We're going to just try to relax the solution concept here and try to solve it. And in fact, I'm going to show you that it is possible to break all these three curses just by using mean field games approximation. And to be more concrete, so let's first consider, say, an agent reinforcement learning problem on the left-hand side. And in this case, each agent I could have its own transition dynamics and rewards. Those could be different. And this will depend on the entire state action information among all agents, right? So this is sort of the most generic setting of an agent reinforcement learning. And if we assume that agents are symmetric in this way that, say, their state dynamics and the reward are the same, and if we net this number of agents n goes to infinity, then we'll be able to obtain a very simple mathematical abstraction of the so-called mean field games, right? In the mean field games, all the individual interactions among agents will now be simplified into the interaction between a representative agent and the rest of the population, okay? And particularly for a representative agent, the state dynamics P and the reward R will not only depend on its current state action and the whole population state action distribution, which we denote as mu here, okay? And I should mention that this mean field game concept has been originally introduced since 2005 by two independent groups, one from Montreal and one from France. And this has been actually studied in many fields, like in stochastic control, in finance, in applied probabilities, and in game theory communities. And in most of the existing literature, they study more continuous time and continuous space models. But here we're going to look into more the discrete time and discrete space models due to the nature of reinforcement learning. Okay. So before I move into the more technical details, maybe I think it's worth to first introduce what are the solution concepts related to these two games, right? The n-agent reinforcement learning and the mean field games. And then we'll be able to understand how these two problems are connected with each other. Okay. Maybe I just quickly stop here to see if there's any questions at this point before I move on. All right, looks good. So let's first again look at this n-agent reinforcement learning problem or n-agent dynamic games problem. And particular here, I'm going to look at the finite horizon setting, right? Where the number of interactions with the environment or the number of place is with horizon h, right? You could also, of course, one could also consider the more infinite horizon discounted settings. So here for simplicity, I would just consider finite horizon, and many of the analysis could also extend to the infinite horizon setting as well. So as we mentioned earlier, in these n-player games, the agent's dynamics or the state transitions will depend on all the state action informations in the system. So is the reward. The reward also depends on each individual agent's state and action information. And since agents tries to maximize its own reward, and this reward can be different among them, a natural solution concept is the so-called Nash equilibrium. And by Nash equilibrium, we mean that at this policy, then no agent has any incentive to unilaterally deviate from the policy, okay? In other words, we mean that no agents can really exploit over others by changing its own policy if other agents fix their policy. And we can define the exploitability here by basically the difference in the value functions when we fix all other agents to be pi star, and we only let agent I to deviate from this policy pi I, right? And we look at the maximum deviation here, and we call this the exploitability, okay? Which we denote as epsilon n here. And if the exploitability is less than equal to epsilon, we say the policy is an epsilon Nash equilibrium. If epsilon is equal to 0, of course, this implies that we have reached at the Nash equilibrium, okay? I should also mention that here we're going to consider Markov policies where at time h, the policy could depend on the current time h, and also the value function vi for each individual agent is just defined as a cumulative reward over this horizon of length h. Okay? So this is basically the definition of Nash equilibrium for an agent reinforcement learning problem. So if we net number of agents n goes to infinity, and if you assume that agents are fully symmetric, meaning that the transitions and rewards are the same, this leads to the mean field games, as we mentioned earlier. And similarly, we can, again, just record the dynamics of mean field games where the transitions will only depend on the population distribution, which is the state action distribution over the entire distribution. So is the reward R. And we can also similarly define the equilibrium here for the mean field games as following, right? We say a policy pi star is a mean field game equilibrium if it is already the best response if all the other agents fix their policy to pi star. So in other words, right, if we let all agents choose policy pi star, and if we consider the mean field, or if we consider the population distribution, fix the population distribution to be mu pi star, then this policy pi star is going to be the best response with respect to this population. So in other words, right, if all other agents fix the policy to be pi star, then no agent can improve further over this policy pi star, okay? So I'm going to use this mu pi to denote just the population evolution distribution induced by this policy pi as in the definition of value function, right? Again, for this setting, the value function is going to be the cumulative reward over the time horizon h, and here reward will depend on the distribution, population distribution at time h. Okay. Of course, in practice, as we mentioned, right, the number of agents may not necessarily be infinite, and also agents may not be exactly symmetric. So we can actually show that even if, regardless of whether agents are symmetric or not symmetric, we can always construct some mean field games by taking some symmetrization operation and lifting the counting space into the infinite agent continuum, right, using some Lipschitz extension. And more specifically, we can actually construct the mean field games the following, right? If you're given some n player reinforcement learning problem where this PI and RI could be different, we can define the mean field games by defining the dynamics P to be the averaging over some Lipschitz extension of the symmetrization of each individual state action. So at high level, this basically means that we wanted to just lift the counting space into the empirical distribution space, right? So the details doesn't really matter here how we define this P and R. In fact, in later, you'll see that we're never going to use this explicit construction of these mean field games. We're going to just use the existence of these mean field games, okay? So in other words, let me just say this one more time, that basically we can show that for any arbitrary n-agent games, we can kind of abstract out some mean field games from it, and we can use this as a good approximation for the n-agent game. So of course, this leads to several fundamental questions. First of all, how good is this mean field game approximation to the n-agent reinforcement learning? How do we define goodness here, and how do we check how this approximation will scale with the number of agents? The second question that we care about is how easy it is to solve these mean field games, right? What are the computational and also statistical complexities of solving the game, the mean field game? Lastly, and also more practically, can we just leverage n-agent simulators to just learn independently to achieve some desired equilibrium instead of having to simulate the whole mean field games? Can we achieve independent learning in this setting? So these are kind of the three overview questions that we'll try to answer in this talk. Okay. So let's first thing first, let's just first look at the approximation side, right? The question here is, how good is the mean field gain approximation to the n-agent gain? And how do we define goodness here? So a natural definition of goodness is just to use exploitability, right? So suppose we're able to solve some mean field games and we can obtain some solution like Nash equilibrium from the mean field games or some equilibrium policy from the mean field games, which we denote as pi star. And we're going to just let these n agents to take this policy pi star. And we want to see, how close is this to a Nash policy, right? We're going to just evaluate this policy pi star and see how large is this exploitability. If the exploitability is small, then that means this pi star, this solution from the mean field games, is already a good approximation to the Nash equilibrium. Okay. So there has been actually a number of existing works that tries to establish these approximation results, but more in the asymptotic sense. And particularly the focus on more stationary setting where the population distribution remain fixed throughout the dynamics. And there are, say, for example, works that consider homogeneous agents or multi-population mean field games, etc. So our focus here is that we wanted to be able to establish non-asymptotic approximation results that will focus on just having finite number of agents n and having finite horizon length h. And also we want to deal with heterogeneous agents as well, not just homogeneous agents. Okay. So here's one of our main results where we've shown that if we just let agents adopt this mean field gain equilibrium, then the n-agent exploitability can be upper bounded by these three terms here, okay? So let me just unpack it for you. So the first term here corresponds to the approximation error due to the fact that we only have finite number of agents instead of infinite number of agents, okay? And as you can see that this first term scales in the order of 1 over square root of n, right? As n goes to infinity, this term will essentially diminishes to 0. You might also notice that this first term also depends on some crucial constant L here. And this L is the Lipschitz constant of the underlying population flow operator that we mentioned earlier, right? This is how your population distribution evolves over time under a given policy pi. So as you can see that if the Lipschitz constant L is small, right, let's say it's less than or equal to 1, then this first term will only have quadratic dependence on the horizon h. In the case when L is very big, right, then this could lead to exponential dependence on h. So the second term in the bound corresponds to the approximation error due to the fact that agents may have different transition dynamics, right? This is corresponding to the dynamic heterogeneity. In particular here, this coefficient alpha describes the degree of dynamic heterogeneity among the agents, which is defined as a maximum discrepancy between individual transition dynamics pi to the mean field dynamics P, okay? As you can imagine that if agents are fully symmetric, then this degree alpha is going to be equal to 0, and this term will also vanish, okay? And in terms of dependence on H, this will have similar dependence as the first term here. And the last term corresponds to the approximation error due to the reward heterogeneity. And here beta denotes the degree of reward heterogeneity, which defined similarly, right? The largest discrepancy between the individual reward and the mean field reward. And you can see that this term will have a much milder dependence in terms of horizon h. So with this result, you can immediately see that if the number of agents n is very large, And if the underlying dynamics is relatively stable, say this constant L is small, then this bound will be very small, right? And this basically means that the mean field gain approximation will be good, right, for the n-agent dynamics, and it is actually quite robust also to small violations of symmetry, right? It's the approximation error is captured by the asymmetry among the agents and also the number of agents in the system. So I should mention that in the exact symmetry case, when alpha and beta is equal to 0, this approximation non-asymptotic bounds is in fact the first, I think, in the literature. And as you can see that in the worst case, this might have some exponential dependence. And we've shown that actually this is not something that you can improve. In fact, we can construct some hard instances where there's no way that you can get rid of this exponential dependence here in the worst case. And for those of you who are more interested in the infinite horizon setting, the stationary mean field game setting, then we also have similar results that shows that the approximation bounds will scale cubically in terms of the effective horizon if the underlying population evolution operator is non-expansive. Otherwise, we might also suffer from much slower convergence if this non-expansiveness does not hold. And the convergence can be, the bound can be arbitrarily bad, okay? So that speaks about the approximation bound. And now let's move to the next question is, how easy it is to solve these mean field games? Okay. Of course, there are two sides of this story here. First of all is, what if we know all the, if we have full information about the underlying model, we know the state dynamics, we also know the rewards, then how easy it is to compute or to find what is the Nash equilibrium for the mean field games. And in fact, there has been a lot of recent research on this topic that look at different settings of mean field games. And oftentimes, one needs to introduce some additional assumptions to show that it is in order to solve this problem. Particularly, for example, in the stationary mean field game settings, if we assume that the underlying population evolution operator gamma p is contractive, then we can show that solving or finding the equilibrium basically reduces to solving logarithmic number of single agent reinforcement learning problem. Or in the final horizon setting, there is work that shows that if the reward is monotone and if the dynamics P has no independence in the density or in the population mu, then you can also reduce to these two just solving polynomial number of policy evaluation steps. If we get rid of these assumptions like contractivity or monotonicity, in our recent work, we've shown that if you only have the minimum assumptions like Lipschitz continuity without any of these contractivity, monotonicity, then this problem can be very hard, right? We've shown that actually this problem can be still PPAD complete, which is as hard as solving some n-agent general sum game problems. So this, in other words, this basically says that if we wanted to achieve some computation tractability, then some additional structure assumption seems to be necessary here. So what about on the statistic side, right? Because in practice, oftentimes we don't really know the model, and we have to leverage data and generate samples from the dynamics in order to try to learn the underlying Nash equilibrium. So in other words, so we want to ask basically how many samples are sufficient in order for us to learn an epsilon Nash equilibrium given some hypothesis class, right? This problem has been extensively studied, of course, in the supervised learning setting and also in the single agent reinforcement learning setting. So in the single agent reinforcement learning setting, it has been shown that both in the tabular settings and also in the functional approximation setting, learning single agent reinforcement learning can be made sample efficient in the sense that the sample complexity will depend polynomial in the underlying size of the problem. or in the function approximation setting, it will depend on the underlying complexity of the function class of either the value functions or the model class. Okay? And there has been a lot of rich results in the past 2 years, in the past few years. And when we move from single agent reinforcement learning to mean field game settings, one would think that the exploration for mean field games will become much more challenging, right? Because now the reward and the also transition dynamics both will depend on the underlying population distribution, which is infinite dimensional, which is no longer under some discrete state action space anymore. So surprisingly, we've shown that actually learning mean field games is statistically no harder than solving a single agent reinforcement learning problem. So here's one of our recent results, where we're shown that if we just make very minimal assumptions on, if we're given some model class M, which contains the true model that we don't know, right? And if you assume that the transition P and R are both Lipschitz continuous, which are the minimum assumptions in order to guarantee already the existence of Nash equilibrium. So under these two basic assumptions, we can show that we can construct some iterative model elimination-based algorithms that achieves a sample complexity only polynomial in the problem, some intrinsic problem dimension, and the horizon H, and some other Lipschitz constants, and 1 over epsilon, okay, with high probability. So that, in other words, if this intrinsic dimension is small, right? If this is independent of your state action space, then this basically means that, statistically speaking, that learning mean field games is indeed tractable, only requires polynomial in time samples. And I will not go into too much details into how we define this intrinsic dimension here. This is just some generalization of the so-called model-based eluded dimension that has been introduced in the single agent reinforcement learning settings. So this basically is the longest trajectories you can use to differentiate different policies. And we can show that this dimension is actually fairly small for many cases. For example, in the tabular mean field game settings, then this dimension is indeed smaller than the size of state times action, the size of the state and action space. And we can also extend this further to the linear mean field games, which is sort of like an extension of the so-called linear MDPs. If the transition P can be factorized as following, then this dimension here will be smaller than, will be upper bounded by the underlying dimension of the feature space, okay? And the takeaway here, as I said, is really that we've shown that although learning mean field games in general can be computationally intractable, but then statistically speaking, this is still a tractable problem. So that basically answers the second question that I introduced, and maybe I just stop here for a second to see if there are any questions at this point before we move on to the third question. Okay.
I mean, I would have some questions, but maybe I can ask at the end to not interrupt you now.
Sure, no problem. Yeah, great. Hope so far so good. So yeah, so now we have seen that mean field games gives us a good approximation, and also, you know, statistically speaking, is not too hard to solve. But of course, in practice, if we wanted to really solve mean field games, this requires us to simulate infinite number of agents, right? It also requires us to track what is the population distribution of those infinite number of agents, which is sort of impractical or unrealistic, right? What we want to do is, like, we just want to simulate or leverage these n agents that we have and see whether they can just run algorithms and they will be able to just achieve the desired equilibrium without any coordination with each other, and they can learn this fully independently. So that is the first question about independent learning. And we've shown that, in fact, this is possible, right? It is possible, and actually you can just deploy very simple algorithms like policy gradient descent, and then you can actually achieve these independent learning guarantees. Let me just be a bit more specific here, right? So the goal here is that we would like to learn from just samples by simulating the n-agent games without really having to construct the mean field games and run mean field game simulations, okay? So the algorithms that we consider here, again, is fairly simple. It's just a naive extension of policy gradient from single agent settings to the many agent setting, right? So basically at every iteration, for every agent, we let them keep their policies fixed, and then each agent will perform some TD learning algorithms or temporal difference learning algorithms in order to estimate their corresponding Q values for each of them, right? Once each agent estimates its own Q value functions, it's going to just consider some policy gradient update using this Q function estimation, which is basically doing the following update where we plug in the QPy and we try to maximize the inner product between these two. And we're going to consider a generalization of gradient descent, which is the mirror descent, where we consider some regularization term, and also the Bregman divergence also in the update rule, okay? And depending on different settings, we might use different regularization parameters. We might use different Bregman divergence as well. Okay, so this is a very generic algorithm scheme here. So what we can show is that under these additional structural assumptions, as we mentioned earlier, that is needed for the computational side, then if we let n agents to run just these algorithms I described there, like policy mirror descent independently, then the algorithm will converge to epsilon close to some Nash equilibrium, some approximate Nash equilibrium within only polynomial in one over epsilon samples, right? And I say this is an approximate Nash equilibrium because remember that there's always this approximation error that we're subject to due to the fact that we only have n number of agents and agents may not be fully symmetric. Okay, so the approximation error is something that I have introduced or characterized earlier in the first question there. And particularly, we can analyze the sample complexities based on different settings, and this will end up with different polynomial, different order of sample complexity. For example, the guarantees will hold for stationary mean field games with regularization. As I mentioned earlier, this is sort of necessary in order to guarantee computation tractability of the setting. Or it also holds for example, stateless mean field games with monotone rewards or finite horizon mean field games with monotone rewards, but with population independent dynamics. In all these settings, we're able to develop the corresponding sample complexities. And one thing particular to note here is that the abstraction of mean field games that we introduced earlier is not used anywhere, okay, in the algorithm, right? We don't really need to construct these explicit mean field games. It's only used as a proof technique in order to show that there is some relaxed solution that the algorithm will be able to converge to, okay? And in particular, like we have also run some experiments to showcase that how the exploitability actually is influenced by the number of agents in the system, right? For example, you can see here that the more number of agents we have in the system, then you will have much smaller exploitability, right? This is largely due to the approximation error. So with that, I think I have sort of hope to convince you that that mean field game seems to be a promising solution to address these three curses. One on the curse of multi-agency, where we have shown that mean field games can be a very good approximation, right? It does not really subject to any scaling in terms of the number of agents in the system, right? It can be a very good approximation if the horizon of the decision-making problem we're looking at is small, and also if agents exhibit some mild asymmetry among them. Also, on the tractability side, we have shown that solving mean field games can be computationally tractable if we consider some additional structure assumptions, and it is statistically tractable under very mild conditions. And lastly, and also more practically, right, solving mean field games can accommodate independent learning algorithms, such as simple policy gradient methods, in order to converge to some approximate Nash policies. And of course, there are still many, many open questions, right? We're just scratching really the surface here, right? As we can see that there is still this significant computational and statistical gaps. Whether this is fundamental or not, it remains unclear. And also, of course, a lot of these results really hinges upon the fact that the asymmetry among agents should be benign, right? Should be very mild. If we're going beyond this benign asymmetry, then it might make sense to group different agents into different classes and then consider more multi-population type of mean field games as a better approximation. And of course, more interesting that can we just consider other type of approximation instead of mean field game approximation, right? What are the other alternatives in order to approximately solve many agent reinforcement learning problems? So with that, I want to quickly point out, so here are the work is based on primarily joint work with my PhD student Batu and my PhD student Jiawei, my former postdoc Sammy, and our collaborators Matthew and Andres, and the papers that I mentioned are listed here. With that, I would like to thank you very much for your attention and for staying with me here. Yeah.